Thanks for the great introduction. Hi everyone, my name is Chang. I'm a third-year PhD student at University of California, San Diego, working with Professor Mingu Kang and Professor Tajana. Today we are going to introduce our work named Hybrid SLC-MLC RRAM Mixed Signal Processing in Memory Architecture for Transformer Acceleration via Gradient Redistribution. So large language models are being widely used these days, and many companies are developing their own generative AI models, which increase the scale of the LLMs. Due to this kind of increasing model size, the computational overhead is becoming a main problem, and also the increasing data size causes the memory wall problem. So to avoid those kind of issues, the processing memory architecture has been introduced. In the conventional way of the von Neumann architecture, the data constantly moves between memory and then processor, which causes the memory wall bottlenecks. On the other hand, in the processing in memory architecture, now the computation can be occurred directly inside the memory, so it can reduce the latency and then the energy from the unnecessary data movement. So among many different types of the PIM architecture, the resistive memory, we call the RRAM, is a good candidate to accelerate the huge scale of large language models due to its many benefits. By using this RRAM, we can compute the Gen-B PIM operation inside the RRAM array. So like for example, when you write the weights on each cell, and then simply activate the word line driver based on the input vectors. Then simply the input voltage will be multiplied by the conductance of each cell. Then the current will be accumulated in the 1-bit line. Then this operation will be the exactly same as the dot product between input and the weight vector as the Gen-B operations. And since we can turn on the many bit lines at the same time, so that we can improve the parallel computation as well. So the benefit of using this analog processing, RRAM processing memory architecture is its high parallelism and also ultra low energy consumption with the high densities to store the weight. On the other hand, we can also implement the digital RRAM PIM operation by selectively turning on the three different bit lines for the neural operation, which can be used for the Gen-V operation. So although the parallelism would be worse than using the analog RRAM PIM, since we don't need the expensive ADC in digital RRAM PIM, so we can deploy this for the operation, which requires the fast and then high bit precision. So there are two types to store the data inside the RRAM. The first one is the single level cell, and the other one is the multi-level cell. So for the single level cell, now we can store the 1 bit inside the one cell. So as you can see in this left figure, it has the high noise margin, so that it has the high reliability with the low bit error rate. And also, we only need to write the 1 bit, so it shows the fast write operation. However, due to the same reason, it can show the low density compared to the MLC storing type. And also, it consumes the higher energy for the PIM operation per bit. On the other hand, for the multi-level cell type, we can now store like more than 2 bits inside the one cell. By doing so, we can have the high density and the low energy for a PIM operation per bit compared to using the single level cell. However, since the noise margin is narrow, it can cause the low reliability with the high bit error rate due to this overhead region. And also, this needs many iterations for writing, so write operation is relatively expensive compared to the single level cell, and also requires the high bit precision ADC, which could be also expensive. And lastly, this multi-level cell can be operated only inside the analog RRAM PIM operation. So these are the two related works which try to accelerate the transformer models by using the RRAM PIM architecture. So first work is the Azadi, which tried to accelerate the attention operation using the mixed RRAM PIM architecture. However, they only implemented the single level cell RRAM PIM, and haven't explored the chance to use the multi-level cell. And the second work is the Sprint, which tried to use the analog multi-level cell PIM operation for the token printing. However, the only small portion of the operation is done with only the analog RRAM PIM, and then they still maintain the expensive digital processor for the attention operation. So in our high flex PIM, we implemented the mixed signal RRAM PIM architecture. So inside the transformer, there are two different types of the linear operation. So first one is the static linear layer, such as feed-forward network or like projection layer. So for this static linear layer, we are implementing the analog RRAM PIM with the hybrid manner of the single level cell and the multi-level cell RRAM PIM architecture. And then for the dynamic linear layers, such as the self-attention, we are implementing the digital RRAM PIM with only using the single level cell. Here, the analog RRAM PIM has its inherent non-ideality. So rather than relying on inherent error resiliency, we try to transform the AI models to have the dominant fraction to be error tolerant by using our proposed gradient redistribution techniques. By doing so, now we can store the dominant fraction of the weight into the efficient multi-level cell instead of using the single level cell. So this is the structure of the encoder model. This encoder model is including the many different operations like self-attention, feed-forward network, and like nonlinear operations such as like softmax. However, most of the operations are general matrix vector multiplication type, which means we can use the processing memory architecture for the high parallelism. So especially for the linear layer, which has the static weight matrix, which means once the weight matrix is written, then it doesn't change during the inference. We can use the analog RRAM PIM operation for the GEM-V, so we can enjoy the high parallelism, and also we can enjoy the chance to implement the multi-level cell. On the other hand, for the dynamically generated matrix during the self-attention, since some of the operations requires the high bit precision and fast write operation, so we implemented the digital PIM, RRAM PIM operation, which doesn't require the expensive ADC with the fast programmability. So for the analog RRAM PIM, we can use the multi-level cell for storing some of the weights matrix. So for example, for the critical weights in the static matrix, we are storing the weights in the single level cell type to secure the accuracy since it has the higher reliability. On the other hand, for the non-critical weights, we are storing those weights in the multi-level cell to improve the area and the energy efficiency, even though it has the low reliability. Then here's one question. How do we distinguish the critical versus non-critical weights? In our work, we implemented the singular value decomposition we call the SVD, and now we can make the weights in the order of the importance. So the initial matrix is now split into three different sub-matrices, U, sigma, and V. And here the sigma matrix is the diagonal matrix with the order of the importance in rank-based. And then we do the matrix truncation to maintain the number of the parameters and then the number of the computation so that we can save the memory. So this shows the gradient of the weight before applying the SVD, where the gradient indicates the sensitivity to the finer model accuracy. So as you can see here, the gradients of each weight are uniformly or randomly distributed. However, after applying the SVD, now the weights with the high rank shows the large gradient. So the motivation from this could be then how can you reshape the model so that the 80 to 90% of the weights can be mapped to the multi-level cell. So this is the architecture of our high flex PIM, where the one high flex PIM chips includes the 24 processing units. And then inside one processing unit, we have 24 analog PIM module to compute the linear layer. And since this is the analog PIM module, it includes the reconfigurable ADC. And also it has the digital PIM module to compute the dynamic linear layer and also to store the tokens. And since this is the digital PIM RRAM PIM module, it doesn't have the ADC, but it does have the special function units to compute the nonlinear operations. So we implemented the SVD truncation and then proposed gradient redistribution technique to maximize our hardware utilization. So to save the storage and also the number of the computation during the inference, we truncate the matrix by using this rank equation. However, the truncation itself can cause a huge accuracy degradation due to much data loss. So we did a fine-tuning to recover the accuracy and then implemented the proposed gradient redistribution to compress the importance into the high rank weights. So by doing so, we could ensure that less than 20% of the weights can have the most of the critical data, which can be mapped to the single level cell. Meanwhile, other weights can be mapped to the efficient multi-level cell. And then we merge the sigma and the V matrix into one matrix for the fast inference. So here, the SVD happens during the fine-tuning with the training dataset only one time, which means later during the inference, since the weights are frozen, there is no additional cost for the SVD and then the gradient redistribution techniques. So after SVD, but without the truncation and doing the fine-tuning, still the high rank would have the high gradient, but the boundaries are still ambiguous. However, after applying our proposed gradient redistribution, now only a few initial singular values have the high gradient, and we can store only this small fraction into the single level cell. So this is how we do the RRAM mapping in like both single level cell and then the multi-level cell. Since we only need to change the parameters inside the shift and adder modules, so we can simply change the data storing type without additional hardware cost. And also which can support the seamless switching between single level cell and the multi-level cell RRAM processing and memory operation. So this is the experiment setup of our work. So we explored the 5 different models, including the encoder, decoder, and the vision transformer. And also for the data type, we implemented integer 8 for all the linear layers, and Q, K, and V tokens, while 14.16 for like other nonlinear operations. And for the hardware baseline, we compare with the 2 state-of-the-art work, and also our in-house near memory processor, and then the non-PIM baseline. And so for the special function unit, we synthesized using the TSMC 65 nanometer CMOS technology at the 1 gigahertz. So this is the result of the accuracy. So as you can see here, for the encoder model, with the 5 to 30% of the single level cell ratio, we can secure the accuracy, so less than 1% of the accuracy degradation. And for the decoder and then vision transformer models, with the only 5 to 20% of the single level cell ratio, we could achieve the negligible loss increasement for the decoder, and then the less than 1% of the accuracy degradation for the vision transformer model. So this shows the impact of the gradient-based protection. So we compare with the 2 different protection methods. So the first one is the magnitude-based one, where the weights with the high magnitude before the SVD are now mapping into the single level cell. And the second one is the rank-based one, where the weights with the high rank after the SVD are now mapped to the single level cell. So as you can see here, the mapping weights with the high gradients after the SVD in single level cell outperforms the rank and the magnitude-based protection method. So this is because only the gradient-based selection reflects the final loss, which enables the better selection of critical weights. So this shows the end-to-end energy consumption. So our high-flex PIM shows 1.67 times and 1.44 times higher end-to-end energy efficiency for the encoder and decoder model versus Asadi work. And this is due to the acceleration for the linear layer using the multi-level cell RRAM PIM operation. And also it shows the like more than 4 times higher energy efficiency for the both encoder and decoder model versus the sprint due to its mixed signal PIM operation. For the speed up, we achieved maximum 1.86 times higher speed up compared to the Asadi due to 2-bit MLC doubling the throughput with the same energy consumption. And also achieved maximum 46 times higher speed up compared to the sprint model because we're using the in-memory computing to remove the redundant data movement. So the conclusion of our work is that high-flex PIM combines the digital and analog RRAM PIM to accelerate the transformer models. And it implements the hybrid single-level cell and multi-level cell analog PIM for better energy and the area efficiency. And we propose the gradient redistribution techniques, which can reshape the weight importance to have dominant fraction to be error tolerant, enabling up to like 70 to 95% of the multi-level cell usage with negligible accuracy loss. So compared to the SOTA models, it achieves up to 1.67 times energy efficiency and 1.86 times the speed up. So and also our high-flex PIM scales efficiently across the multiple processing units and chips with the minimal overhead. So yeah, this is the end of my presentation, and thanks for listening.